Good afternoon, everyone. We are reviewing Chapter 4 of Wetzel's Limnology textbook, edition number 4. And where we left it at last time was distribution of inland surface waters. We were about to embark in river and stream characteristics. But before we do so, let's look at a couple tables and figures. The first table that I'd like to look at is listing the number of lakes by surface area size class and by continents. So this is the number of lakes by 1,000. So we have a lot of lakes that are between 0.1 and 1 in kilometer squared in surface area. So we have 1,241 by 10 to the 3, the number of lakes in that surface area class, where we have a very small number of lakes that are greater than 10,000 kilometers squared. We only have 0.018 by 10 to the 3 of those lakes. In terms of continent distribution, the lion's share of the number of lakes by surface area is North America, then Europe, Asia, South America, Africa, and Oceania. And then by volume, the Caspian Sea takes the lion's share. So the Caspian Sea has a total volume, and then once again here it's by 10 to the 3 of 75.6 by 10 to the 3 kilometers cube of water. Lake Baikal, 23.6, Lake Tanganyika, 18.9, Lake Superior, Lake Malawi, Lake Michigan, Lake Huron, Lake Victoria in Africa, Great Bear Lake in Canada, and the Kara-Bogaz Gull Lake. The next figure I'd like to look at is a figure that shows the lakes in proportionally by surface area and their distribution in the world. And so what they did here is the red color indicates loss of surface area, and the blue colors indicate gain in surface area over the time between 1984 and 2019. So this RRC has experienced catastrophic reductions in area because of diversion of waters for agriculture. The Amazon basin is drawn for size comparison, and lake names in italics indicate human-made reservoirs. Lake Vostok in Antarctica is a subglacial lake. So as we just saw here, the figure 4-3, we have the Amazon River by comparison that shows there its surface area, and everything as the figure says is up to scale. We can see that the Chad Lake in Africa actually has gained surface area. It's blue, while the RRC has lost surface area. It's in red. The Caspian Sea, as we just saw in the table above, it takes a lion's share in terms of surface area. And then we have Lake Michigan, Lake Superior, that shows pretty large lakes, the Great Bear Lake, the Great Slave Lake in northern Canada. And we have Lake Victoria in Africa, we have Lake Malawi, Lake Baikal here in Siberia, which is located right here. So we can see the lakes on the map of the world here. So this is the Caspian Sea. These are the Great Lakes here, and we have those Canadian lakes, the Great Bear Lake, the Great Slave Lakes, and the likes. Then the next figure that I would like to look at distributes the lakes by either freshwater lakes or saltwater lakes. So on the right, we have a distribution of large water lakes, freshwater lakes, and so for a total number of lakes, right? So the global distribution of water volume stored in lakes and reservoirs with a surface area of at least 10 hectares. Total volume is 187,900 kilometer cube. So large freshwater lakes, Lake Baikal, we have 13%, Lake Tanganyika, 10%, Lake Superior, 6%, Lake Malawi, 4%, other natural large freshwater lakes, 13%, large reservoir, 2%. Then we have the medium lakes in green, natural lakes, 5%, and then actually the reservoirs are taking about 1%. Then the small lakes, 2%. Then the large saltwater lake with the Caspian Sea at 41%, the other large salt lakes at 3%. Then I wanted to look at figure 4-5, and we have two graphs here. So on the left, we have the graph of the number of lakes by surface area, and on the right, we have the number of lakes by volume. So that reflects what we just saw in the table above, so where we have a large number of lakes with small surface area, and we have a small number of lakes with large surface area. And the same kind of type of distribution is presented in terms of volume. We have a large number of lakes with small volumes and a small number of lakes with large volumes. So why don't we get into that section here. River and stream characteristics. Rivers are watercourses that flow over the land surface, eventually entering lakes or other rivers at confluences. River systems are formed by a network of connected tributaries that drain toward a common main stem and typically discharge into the ocean. Some rivers end at an inland depression, often represented by an endorheic lake. So an endorheic lake is a lake that does not discharge to a sea or an ocean. In arid or karst region, rivers can terminate without reaching a confluence or endorheic lake if their waters evaporate, infiltrate into the ground, or enter sinkholes or caves to continue underground. The water flowing through rivers is originally provided by precipitation that falls over the drainage basin, which then, depending on environmental conditions, may transition through melting, soil infiltration, and groundwater recharge processes before entering the river channel as land surface runoff or groundwater-based flow. Affected by diverse hydrologic and geomorphologic influences, the world's rivers display varied physical, chemical, and biological characteristics. Many expressions exist for smaller rivers, including streams, brooks, and creeks. Following natural scaling laws, the number and combined length of small streams exceed those of large rivers. Their location within the upstream headwater parts of the drainage basin is reflected in their limited flow quantity, drainage basin area, and high average elevation. While more streams are generally found in regions of higher humidity, stream length and density dynamically adjust when drainage basins become wetter or drier over seasons and precipitation events. For example, river networks extend and retract as stream channels alternate between flowing and drying phases. A. Running waters, lotic ecosystems. Rivers and streams within their drainage basins are central to surface water ecosystem. A number of characteristics differentiate running waters from lake ecosystem. Flowing freshwater environments are called lotic, lotus from lavo to wash, which refers to the unidirectional water movement along a slope in response to gravity. Lotic ecosystems are contrasted to lentic, lenis to make calm, or lake ecosystems. The directional movement of water is a fundamental property of lotic ecosystems. In fact, the importance of variable and typically rapid throughput of water and materials contained in it is evident in the biology of most organisms inhabiting running waters. Dissipation of energy from moving masses of water affects the morphology of streams, sedimentation patterns, water chemistry, and the biology of organisms inhabiting them. When the energy of flowing water is abruptly dissipated, as in the transitional zone between a river and a lake, the change from lotic to lentic characteristics is rapid. Most lakes are open and have distinct flows or fluxes through and out of them, which can be variable and are often low in comparison to the lake's water volume. Thus, the main distinction between running waters and lakes is focused on the relative residence times of their waters, also called turnover times, or the related water renewal rates per unit time. Residence time is defined as the ratio between storage volume and mean through flow, and is generally much shorter in rivers than in lakes, where it can exceed 100 years in large lakes. Not all rivers and streams show continuous surface flow throughout the year. Water ceases to flow for at least 1 day per year along 51 to 60% of the world rivers by length. The frequency, duration, and timing of flow cessation and resumption are the main determinants of the ecology and biogeochemistry of those non-perennial lotic ecosystems. In some cases, surface water persists in pools of standing water, but without flow resumption, water eventually evaporates or infiltrates, and river channels can fall dry for extended periods of time. Most rivers and streams in semi-arid and arid landscape are non-perennial, but flow cessation is also common in small streams across more humid climates. So I wanted to go over some of the pictures I took in Alaska a few days ago of different types of streams and rivers. So this is just a first order stream here in Alaska. And this is the same stream. This is actually a drone video taken of the stream itself. And you can see that there was actually an ice dam that broke, and that created all this ice on this trail here. So once again, this is a first order stream. This is the Matanuska River as it reaches what is called the Knik Arm in south central Alaska. And this is a typical pattern of a braided channel. And then this is the same river, a little upstream of it, was the braided channel pattern. So I thought you'd be interested with these pictures.